Okay, children, good morning, all of you. In previous class, we have discussed general types of chemical reactions, chemical combination, chemical decomposition, chemical displacement, and chemical double displacement. Double displacement or double decomposition reactions. Okay. Here, next category, combustion reactions. Combustion reaction. Combustion reaction means whatever the substance, whether metal or non-metal, combined with oxygen. The substance combined with oxygen, it produce a new compound with heat and light. Then those reactions are called combustion reactions. Here, this is metal oxide, this is a non-metal oxide. So here, whatever the substance in the presence of oxygen, combustion reactions also known as burning reactions. Here, burning in the presence of oxygen, combustion in the presence of oxygen, they produce their oxides and they liberate heat and light. That type of reactions are called combustion reactions. Look at the examples. Here, carbon combustion, sulfur combustion, here magnesium combustion. Here, these produce what? Carbon dioxide, sulfur dioxide, here magnesium oxide, and they produce heat. They produce heat. Here, Q represents heat, general representation of reaction. Okay, these are called combustion reactions. Here, in combustion reaction, the substance which undergo combustion, those are called combustible substance. Combustible substance means the substance which can undergo or which can combine with oxygen, they produce heat and light. Those substances are called combustible substance. Here, which do not react with oxygen, those substances are called non-combustible substances. Okay. Next, if you observe the reaction, they liberate what? Heat and light. Whether in the form of heat or light, energy is liberated based on the energy liberation. Those are called exothermic or endothermic reactions. Exothermic or endothermic reaction. Exo means heat is liberated. Here, endo means heat is absorbed. For example, here C plus O2 gives rise to CO2. Look at this. Here, this is combustion reaction and heat is liberated. Here, a representation of exothermic reaction. Look at this. C plus O2 gives rise to CO2 plus Q. Here, heat is liberated. Product side with plus symbol. It is also represented like this. C plus O2 minus Q gives rise to CO2. Both are same. Here, product side plus Q, reactant side minus Q. Another type of representation, C plus O2 gives rise to CO2. Here, delta H is equal to negative. Heat is liberated. This is delta H represents reaction enthalpy. These three are same representations. All are represent exothermic reactions. Once again, exothermic means energy is liberated. Energy is liberated, released. Here, released means product side plus, reactant side minus, reaction enthalpy negative. All are same representations. Similarly, in the case of endothermic reaction, endothermic means what? Heat is absorbed, heat is required, energy is required. In the case of carbon plus sulfur gives rise to carbon sulfide CS2. In this case, look at this, product side minus Q. Here C plus S plus Q gives rise to CS2, or C plus S gives rise to CS2, and delta H is equal to positive. Product side minus, reactant side plus, or delta H is equal to positive. Here all are same representations of endothermic reactions. Energy is absorbed. Energy absorbed. Here these are exo and endothermic reactions now. And one more type of reaction, reversible and irreversible reactions. Some reactions are reversible. Look at this. Reversible, irreversible reactions. Reversible reactions means, for example, here a reactant A plus B gives rise to C plus D. Here A plus B, these are reactants which are involved in the reaction. These are products. In some reactions, here products are able to form reactants again. Products are able to combine together to form reactants again. Here it consists of two different types of reactions. Here A plus B gives rise to C plus D. This is a forward reaction. C plus D gives rise to A plus B. This is called backward reaction. So forward reaction, products are formed. In backward reaction, reactants are formed. That's why these type of reactions are called reversible reactions. For example, here H2 plus N2 gives rise to NH3. Here this is a reversible reaction. Here these reversible reactions, most of the cases are carried in closed vessels. Closed vessels only. If the products are escaped from the reaction mixture, a reversible reaction not taking place. That's why those reactions should be carried in the closed vessels only. So reversible means the products are able to combine together to form reactants again. Those reactions are called reversible reactions, and this is the symbol. Here forward arrow mark, backward arrow mark. These are the representation of reversible reaction. For example, CaCO3 gives rise to CaO plus CO2. Here CO2 is a gaseous substance. Here upward arrow represents gas. This is solid. This is solid. When we heat this, here CO2 is escaped in a open vessel. CO2 is escaped from the reaction mixture. Then there is no backward reaction. This type of reactions are called irreversible reaction. Irreversible means only forward, single arrow towards products. These reactions are called irreversible reactions. The gas released or gas escaped from the reaction mixture, precipitation reactions, and these all comes under irreversible reactions. Okay, next, another type of reaction, catalytic reactions. Catalytic reaction means catalysts are used. In language of chemistry, we discussed now. Here, in the preparation of Haber process, N2 plus H2 gives rise to NH3, ammonia preparation reaction. In this reaction, here iron acts as a catalyst. Catalyst means what? Catalyst is the substance, external substance, which is added to the reaction mixture to speed up the reaction, or which alter the reaction, not actual speed up the reaction, here which alter the rate of the reaction. It may be increase the rate of reaction or decrease the rate of reaction. That's why here catalysts are of two categories. One is a positive catalyst, another one is a negative catalyst. Positive catalyst means the catalyst which increases the rate of reaction. For example, here iron in the preparation of ammonia in Haber process, iron acts as positive catalyst. That means it increases the rate of reaction, it speeds up the reaction. In the case of H2O2 decomposition, look at this H2O2, hydrogen peroxide, H2O plus O2. In decomposition of H2O2, here phosphoric acid H3PO4. If we add phosphoric acid, it decreases the rate of reaction. Phosphoric acid decreases the rate. That's why it comes under which category? Negative catalyst. Positive catalyst, negative catalyst. Positive catalyst increases the rate of reaction. Negative catalyst decreases the rate of reaction. Here, there are some more substances. Here, look at this molybdenum. Here, molybdenum acts as a promoter. It is not a catalyst, but it enhances the catalyst activity, which boosts the activity of the catalyst. These substances are called promoters. And there are some more substances, those are called inhibitors. Inhibitors are poisons. Inhibitor or poison. Here, the substance arsenic oxide. Arsenic oxide. In the preparation of sulfur trioxide, SO2 plus O2 gives rise to SO3. In this reaction, here AS2O3, here vanadium pentoxide, asbestos. These are the promoters. Here, in the presence of arsenic oxide, it decreases the ability of the catalyst. Here, promoter enhances the ability of the catalyst. Here, inhibitor decreases the ability of the catalyst. These are called poisons also. So, here catalytic reactions, positive catalyst, negative catalyst. Positive catalyst increases the rate of reaction. Negative catalyst decreases the rate of reaction. Promoter enhances or boosts the catalyst. Inhibitor decreases the ability of the catalyst. Here, Haber process, iron catalyst, molybdenum promoter. Here, decomposition of the H2O2, phosphoric acid, acts as a negative catalyst. Here, arsenic oxide acts as a inhibitor. Okay, now? Here, next, another type of chemical reactions. Those are redox reactions. Redox reaction. In redox reactions, redox, look at this word, redox. It consists of a reduction and oxidation, both. Redox means it consists of reduction, oxidation. Look at the reduction and oxidation. Here, reduction. Here, with respect to oxygen or with respect to hydrogen. Look at this. With respect to oxygen, removal of oxygen, addition of hydrogen, addition of electron. Here, addition of electropositive element, removal of electronegative element, and decrease in the oxidation state. These are all reduction reactions. Removal of oxygen, addition of hydrogen, addition of electron, addition of electropositive, removal of electronegative elements, decrease in oxidation state. Obviously, what is oxidation? Exact reverse process. Now, look at this. Oxidation means addition of oxygen, removal of hydrogen, removal of electron, removal of electropositive, removal of electropositive element, addition of electronegative element, increase in oxidation state. These are all comes under reduction and oxidation reactions. Let us check now some examples. Here copper oxide plus hydrogen gives rise to copper plus H2O. This is very basic example. Look at that example here, copper oxide, cupric oxide plus hydrogen, copper plus water. Here this is the reactant, copper oxide converted to copper. During this conversion, what happened to this substance? Here oxygen is eliminated. Here hydrogen converted to water, H2 converted to H2O. What happened to hydrogen during this conversion? Here oxygen is added. So oxygen removal of oxygen is called what? Reduction. Here addition of oxygen, oxidation. So here redox reaction means it is a single reaction, not different reactions. Simultaneously, in a single reaction, reduction as well as oxidation, both processes taken place. Reduction and oxidation, both processes taken place simultaneously in single reaction. Those reactions are called redox reaction. Why? Because if one substance undergo oxidation, obviously another substance undergo reduction. If one substance undergo reduction, another substance must undergo oxidation. That's why those reactions are called redox reactions. From the reaction with respect to oxygen, with respect to hydrogen, with respect to electron, with respect to oxidation state, we can understand whether the substance undergo oxidation or reduction. Here, removal of oxygen is nothing but reduction. Addition of oxygen is nothing but oxidation reaction. In order to understand the oxidation state, increase in oxidation state or decrease in oxidation state, here there are some set of rules. Here oxidation number. Oxidation number. Oxidation number means, for example, here H2O is there. It is the compound. Here hydrogen element is there. Oxygen element is there. Here the apparent charge present in the compound. Apparent charge of the element in the compound. In the elementary form, always that is 0. But in the compound form, the charge present on the element in the compound. Apparent charge present in the element in a compound. Here in this compound, hydrogen apparent charge +1. Here oxygen apparent charge -2. We can understand the here change, oxidation state change or oxidation number with respect to here electrons number. The number of electrons lost or gained or shared. That is nothing but oxidation number of that element. In the elementary form, elementary form means look at this: hydrogen, oxygen, O3, N2, sodium. These are all what? Elements. Elements means always 0. Why? What is the reason? In elementary form, there is no change in the oxidation state. There is no change in the number of electrons. There is no charge. That's why oxidation number of the element, whatever the element in the elementary form, 0. These always exhibit what? Oxidation numbers in what? Compounds only. That's why to determine the oxidation state or oxidation number of the compounds, here we have some set of rules. Here in elementary form, that is always 0. Here 1A group elements, here the oxidation state is always +1. Here 1A group elements means what? Lithium, sodium, potassium, rubidium, cesium, always +1 in their compounds only. Here oxidation state always exhibit in compound form. Okay, now here the 2A group elements always +2, and here hydrogen always exhibit +1 with metals and -1 +1 with non-metals, and here -1 with metals. Here oxygen always exhibit -2 in oxides. Here -1 in peroxides. Here -1/2 in superoxides. Here +1 +2 with the fluorine. Oxidation states, different oxidation states. -2 with oxide, -1 with peroxide, -1/2 in superoxide, +1 or +2 in with fluorines only. Fluorines. Here fluorine always exhibit -1 because it is the element with the highest electronegativity. This is the only element now. Only -1 oxidation state. Here, in the case of neutral molecule, the sum of the oxidation states always 0. In the case of ion, the sum of the oxidation states of ion always is equal to its charge. Is it clear? These are the rules to determine the oxidation state of the elements in their compounds. Once again, elementary form always 0. 1A group elements always exhibit +1. A group elements, what are those? Lithium, sodium, potassium, rubidium, cesium. 2A group elements, beryllium, magnesium, calcium, strontium, barium, radium. 2A group elements always +2. Hydrogen, it exhibits two different types. +1 with non-metals, -1 with the metals. Oxygen, different oxidation states. Oxides -1, peroxides -1, oxides -2, peroxides -1, -1/2. Superoxides with the fluorine +1 or +2. Here molecule case, neutral molecule case, oxidation state, sum of the oxidation states should be equal to 0. In ions, whether positive ion or negative ion, the total charge is nothing but what? Sum of the oxidation states of all the atoms present in the ion is equal to its charge. Is it clear? Okay, these are the rules to determine the oxidation states of elements. Here, look at this K2Cr2O7. In this, potassium, chromium, and oxygen are there. Here, this is a unknown oxidation state, chromium. Here, potassium, 2 into +1. Why? Potassium belongs to 1A group element. Plus 2 chromium, 2 into unknown X. plus 7 oxygen minus 2. Here this total molecule, neutral molecule, that's why sum of the oxygen states should be equal to 0. If you simplify this, you get x is equal to plus 6. That means oxygen state of chromium is plus 6. In this way, we can calculate the oxidation state of the elements.